Now that we have a good understanding of Snell's law, something we need to touch on is called the critical angle. So if I have a boundary here with some light coming in, and I'll draw my normal line, let's look at the special case where theta 2 is 90 degrees. I'm going to call theta 1 equal to theta c, which is going to mean the critical angle. And this is what we're going to look at. And let's pretend that we're going from water into air. So the refractive index of air, n equals 1, and water, n is 1.3. If we put this into Snell's law, n1 sine theta 1 is n2 sine theta 2. I want to solve for theta 1 because that's what we're interested in. Sine theta 1 is n2 sine theta 2 over n1. And remember, the opposite of sine of theta is inverse sine of theta. So theta 1 is inverse sine of the whole thing over here, n2 sine theta 2 over n1. Now let's put in our data. n1 is where we're coming from, the water, that's 1.3. n2 is where we're going, that's 1. And this expression over here, sine of 90 degrees, is also 1. If we go back to our unit circle definition, 90 degrees is here, sine of 90 degrees is 1. So altogether we have theta 1, which is theta c, because that's how we defined it, is inverse sine of 1 over 1.3, which is about 50 degrees. If we use the exact same setup now, but we increase the angle of incidence to over 50 degrees, something really interesting occurs. And the light is completely reflected. It doesn't cross the boundary. And we call this phenomenon total internal reflection. So if you're ever lucky enough to go swimming with a turtle, you can say, wow, I love physics. Look at this total internal reflection in action. And while we're on the subject of light interacting at a boundary, and some names for certain angles, there's another special angle called the Brewster Angle or Brewster's Angle. And if light strikes a boundary at the Brewster's Angle, which is called traditionally theta p, the reflected ray and the refracted ray will be 90 degrees apart. But that's not all. The light that's reflected off of this boundary will be linearly polarized. So that is one way to create this polarization phenomenon that we talked about in our last video. So that was just an interesting phenomenon that I thought might be worth talking about. As always, thank you for watching this video, and if you have any questions, feel free to email us using the link in the description.